Welcome. We begin today's session. We will begin by a quick recap of what we have covered in the last session and then proceed to the new topics in today's class. In the last session, we had looked at some of the Z-transform properties. We had also looked at Z-transform pairs. So if you look at it in terms of what is there in the textbook, we have covered what is covered in section 1, 2. We have skipped section 3. We're going to do section 4. Today we will be doing 4 and 5, and then and then we will go back to section 3. As I mentioned, section 6 is something that we will not be covering in this course. So only sections 1 to 5, and we plan to give you a comprehensive view of what the Z-transform can be done. If you remember, we did this example where we wrote down a transfer function. There were 2 zeros and 3 poles. We said that we will do a partial fraction expansion and then compute the corresponding sequence corresponding to this Z-transform. Now, this example has got a lot of value in terms of additional points that we can use this to reinforce. So let us take the first of the additional information that we can gain from here. Okay, so the first task is obtain the ROC for which the DTFT exists. The ROC and the sequence, okay, and sequence x of n, for which the DTFT exists. Okay, first point that for DTFT to exist, the ROC must include the unit circle. So the region of convergence that includes the unit circle is ROC3, where mod z is greater than 0.9, less than 1.5. Okay. Now, how many poles are to the right and how many poles are to the left? We have 2 poles which are to the right, 1.5 and 3 are and minus 3 are on the other side, and then you have 0.9 on one side. So mod z greater than 0.9 means that sequence will be right-sided. So the corresponding sequence h of n, you can write down by inspection, will be equal to A3, right? A3 is the one that is A3 0.9 raised to the power n u of n. Right-sided sequence corresponding to the pole at 0.3. The other 2 will be left-sided sequences, minus A2, 1.5 raised to the power n u of minus n minus 1, minus A1, minus 3 raised to the power, minus 3 raised to the power n u of minus n minus 1. Okay, so you can please verify that this is the sequence, the ROC that and this includes the unit circle, which means that the DTFT exists. Okay, so there is a very useful thing for us to look at the ROC and find out which is the ROC of interest. So the DTFT exists for this, and it does not exist for any of the other ROCs because they will not include the unit circle. Another important thing that we will always look for in transfer functions is what is called a pole zero plot. A sketch of the poles and zeros of the transfer function. Now, you may be typically used to looking at a transfer function and then saying, okay, in this case there are 2 zeros, 3 poles. So therefore, what are the poles and zeros? So let's just mark it down. So we will say that the zeros are at z equal to minus 4 and z equal to minus 2.5. Okay, so notice that I have introduced the 2 zeros here. So this is a 0 and this is a 0. An X is indicative of a pole, a 0 indicating of a 0. So there are two zeros, minus 4 and minus 2.5, and there are poles which we have already, indicated here. So I won't write it again. We can go back and look at, these are the poles, and the poles have already been marked in the figure at minus 3, 1.5 and 0.9. Now, one point to note is that when you have transfer functions, it is always important to understand when we are talking about poles and zeros in the context of the Z transform, important to note the following. So supposing I were to ask you what are the poles and zeros of this transfer function. So H1 of Z, these are examples. H1 of Z. This is equal to 1 plus 4 Z inverse. Okay, this is the one of the terms which is in the numerator. I've just taken only that as the, so you will readily tell me that there is a 0 at Z equal to minus 4, and which is correct statement. Now look at this same expression. I'm going to rewrite it in the following form: 1 plus 4 by Z. This can be written as Z plus 4 divided by Z. Okay. Now tell me, does this transfer function have a pole? The answer is yes. Does it have a 0? Yes, it has a 0 at the same location, 0 at Z equal to minus 4, but there is also a pole at Z equal to 0. So we should never forget that this transfer function has both a 0 and a pole. Okay, something that you should keep in mind. Let's take another example. H2 of Z. H2 of Z, I'm going to take the first denominator term in the transfer function, 1 plus 3 Z inverse. Notice that I can write this as Z divided by Z plus 3, which will tell me that there is a pole at Z equal to minus 3, but there is also a 0 at Z equal to 0. So there is a very important principle that you will find, that when we write down these transfer functions in the Z domain, the number of poles is equal to the number of zeros in the finite Z plane. In the finite Z plane. What do you mean by finite Z plane? Z going from 0 all the way up to infinity, but not including infinity. So, in the finite Z plane. Okay, let's look at one more example, and then it will become very clear. So H3 of Z, I'm going to take it as a ratio of 1 plus 4 Z inverse divided by 1 plus 3 Z inverse. Okay, this one I can write as Z plus 4 divided by Z into Z plus 3, numerator is Z. Notice that Z and Z will cancel, pole 0 cancellation. Remember, that's an important element, leaving you with the following conclusion for this transfer function. There is a pole at Z equal to minus 3, there is a 0 at Z equal to minus 4. We don't have to worry about the pole and 0 at Z equal to 0, that got cancelled, so therefore we don't need to worry about it. But the important thing is the number of poles and number of zeros are the same. Okay, so here is the generalization. In general, supposing I have a transfer function of the form H of Z, which is a product of first order term, k equal to 1 through m 1 minus ck Z inverse divided by m equal to 1 through n 1 minus dm Z inverse, and let n be greater than m. Number of the denominator polynomial is of a higher order than the numerator polynomial. Now, how do we write down the zeros here? Okay, first of all, let's write down the poles. The poles are at Z equal to dm m equal to 1 all the way through n. Okay, that's done. Now let's look at the zeros. The zeros are at z equal to ck, k equal to 1 through m. But m and n are not the same, right? M is less than n. So then we say that there will be n minus m zeros at z equal to 0. Okay, so basically to balance out, you have m zeros at these locations. There are n poles, and where are the additional zeros? They will occur at z equal to 0. Okay, so now let us go back and correct or look at this particular term. There are 3 poles indicated here, only 2 zeros. Where is the third zero going to happen? The third zero is going to happen at z equal to 0. Then you will find that you have 3 zeros and 3 poles. So you can add here that there is a 0 at z equal to 0. That is because of the third order denominator and second order numerator. There will be one additional 0 that we have to account for. Again, the important thing to note is how to draw the pole 0 plot. Identify the poles, identify the zeros, then check if the number of poles is equal to number of zeros, and then write down, if there are any things that are missing, it is probably a 0 or a pole at the origin. Make sure that you indicate them and suitably represent those values. And typically, if you have more than one 0 at a location, let us say there's a double 0 at a particular location. So what you would do is, okay, let us say that there is a double 0, then you would indicate it as just 2 circles, and you can indicate that 2 zeros. You can indicate how many zeros are present. You don't have to draw more than 2. Just show that there are more than 2, and then indicate that there are 2 zeros there. Okay, I hope you are comfortable with this. This is a sketching the pole 0 plot, identifying where the poles are, where the zeros are, and whether there is a pole or a 0 at the origin. Those are important for us to be able to identify. We start with an example that we have already looked at. X of n is equal to u of n, and the corresponding z transform, you can write it down and you will get x of z equal to 1 over 1 minus z inverse. ROC will be mod z greater than 1. Okay, we have another sequence, x of n, which is minus u minus n minus 1. This will have the same x of z, 1 minus z inverse, but the ROC will be a left-sided sequence, mod z less than 1. The pole is at z equal to 1, and we get the 2 sequences. Okay, now I want you to tell me what will be the z transform. I would like you to do it by inspection, equal to u of minus n. Okay, u of minus n. Now, if I were to call this sequence as x1 of n and x2 of n, okay, what is the relationship between x1 of n and x2 of n? Okay, I want you to be able to think along those lines and then write down the expression. Okay, so easiest way is if you can sketch it. U of minus n minus 1 will be like this. It has zeros, all these points. It has got minus 1 in all these values. Okay. Now, u of minus n. U of minus n has got non-zero values starting from n equal to 0. Okay. These are 0 values. So, this is u of minus n, time reversed version of that. And you can easily write down the expression. But what I want you to do is to think of what is the relationship between these two sequences. So if this is x2 of n, this is x1 of n, tell me what is the relationship? x2 of n is equal to minus x1 delayed by 1 unit of time, right? So shifted to the right by 1 unit of time, that basically, and with a negative answer. So if you, once you get this relationship, then you can say that for this particular sequence, the x of z from the previous line will be minus 1 over 1 minus z inverse, but it is shifted to the right, so it will be multiplied by z inverse. So it will be minus z inverse divided by minus z inverse divided by 1 minus z inverse. You can please check that you are getting this relationship and verify that this is a. So again, the ability to shift and to look at, and by the way, what is the ROC? When you shift, the ROC does not change, right? So you have to be always very careful to make sure that you get the correct expression. So in this case, if this is Rx1, this will also be Rx1. Is that correct? You are saying that it is mod z less than 1. Okay. Now, am I allowed to go to 0? Am I allowed to go to 0? Think about it. You have to answer that question for me, and then let me know whether this can go all the way to 0, or you have to restrict the term from going all the way to 0. So again, let me put this as a question mark. Is this true, or is it just mod z less than 1? Okay, which way do you think it is going to be? Okay, it turns out that this is the correct answer, because when you write down the x of z, the easiest way to check is to write down the x of z. X of z is 1 plus z squared and so on. Okay, so z equal to 0 is not a pole. It has got a value equal to 1. So therefore, z equal to 0 can be included. So the region of convergence is mod z less than 1.